In particle physics, the electroweak interaction is the unified description of two of the four known fundamental interactions of nature: electromagnetism and the weak interaction. Although these two forces appear very different at everyday low energies, the theory models them as two different aspects of the same force. Above the unification energy, on the order of 100 GeV, they would merge into a single electroweak force. Thus, if the universe is hot enough, then the electromagnetic force and weak force merge into a combined electroweak force. During the electroweak epoch, the electroweak force separated from the strong force. During the quark epoch, the electroweak force split into the electromagnetic and weak force. Sheldon Glashow, Abdus Salam, and Steven Weinberg were awarded the 1979 Nobel Prize in Physics for their contributions to the unification of the weak and electromagnetic interaction between elementary particles. The existence of the electroweak interactions was experimentally established in two stages. The first being the discovery of neutral currents in neutrino scattering by the Gargamel collaboration in 1973, and the second in 1983 by the UA1 and the UA2 collaborations that involved the discovery of the W and Z gauge bosons in proton-antiproton collisions at the converted superproton synchrotron. In 1999, Gerardus T. Hooft and Martin S. Veltman were awarded the Nobel Prize for showing that the electroweak theory is renormalizable. Formulation: mathematically, the unification is accomplished under an SU times U gauge group. The corresponding gauge bosons are the three W bosons of weak isospin from SU, and the B boson of weak hypercharge from U, respectively, all of which are massless. In the Standard Model, the W plus or minus and Z0 bosons, and the photon, are produced by the spontaneous symmetry breaking of the electroweak symmetry from SU times UY to UEM, caused by the Higgs mechanism. UY and UEM are different copies of U. The generator of UEM is given by Q equals Y, 2 plus I3, where Y is the generator of UY, and I3 is one of the SU generators. The spontaneous symmetry breaking causes the W3 and B bosons to coalesce together into two different bosons, the Z0 boson, and the photon as follows, where theta W is the weak mixing angle. The axes representing the particles have essentially just been rotated, in the plane, by the angle theta W. This also introduces a discrepancy between the mass of the Z0 and the mass of the W plus or minus particles, W1 and W2 bosons, in turn, combine to give massive charged bosons. The distinction between electromagnetism and the weak force arises because there is a linear combination of Y and I3 that vanishes for the Higgs boson. UEM is defined to be the group generated by this linear combination, and is unbroken because it does not interact with the Higgs Lagrangian. Before electroweak symmetry breaking, the Lagrangian for the electroweak interactions is divided into four parts. Before electroweak symmetry breaking, the term describes the interaction between the three W particles and the B particle, where in the mass terms where the sum runs over all the fermions of the theory, and the fields, and are given as the neutral current and charged current components of the Lagrangian contain the interactions between the fermions and gauge bosons, where the electromagnetic current and the neutral weak current are, and under the fermions electric charges and weak isospin. The charged current part of the Lagrangian is given by contains the Higgs 3-point and 4-point self-interaction terms, contains the Higgs interactions with gauge vector bosons, contains the gauge 3-point self-interactions, contains the gauge 4-point self-interactions, and contains the Yukawa interactions between the fermions and the Higgs field. Note the factors in the weak couplings. These factors project out the left-handed components of the spin or fields. This is why electroweak theory is commonly said to be a chiral theory.